Hey everyone, and welcome to this explainer. If you've been watching the news lately, the whole world of artificial intelligence can feel, well, incredibly fast, chaotic, and frankly, a bit overwhelming. We're constantly hearing about massive models, autonomous agents, complex algorithms, and it's super easy to feel like you've arrived late to a conversation where everyone else is speaking some kind of secret language. But today, we're going to slow things right down. We are going to demystify AI, not by throwing a bunch of technical jargon at you, but by building it up layer by layer, starting from the absolute simplest first principles of how we understand the world. To do that, I want to start by asking a very human question. Why do so many people fear mathematics? And in that same vein, why do so many of us feel intimidated by the rapid pace of AI? Usually, it's because we're taught to see these things as, like, mystical barriers. A test of raw intelligence where you either just get it or you don't. We panic because we see a wall of complex symbols, or we hear terms like deep learning, and we just naturally assume there's some kind of magic happening behind closed doors.
But what if we completely flip that paradigm on its head? What if mathematics isn't some mystical barrier at all, but simply a tool we invented to describe the repeating patterns of our everyday lives? And what if AI is literally just a machine using that exact same language to learn from experience? Suddenly, it's not magic anymore, is it? It's just structured observation.
So, here's our roadmap for today's journey. 1. The language of patterns. 2. Learning from mistakes. 3. The architecture of AI. 4. Building AI agents. And finally, 5. Trust and human judgment.
Okay, let's dive right into Section 1, the language of patterns and how we go about translating reality.
Our very first stop is figuring out how we even begin to talk to a machine. And honestly, the foundation of AI is incredibly simple. Before a machine can learn anything, it needs to be able to see the real world. And we do this through measurement. Let's say you're building a movie recommendation system. You don't feed the machine vague, fluffy words like, oh, this person likes fun movies. No, you convert their behavior into structured numbers. So, Person A watched 8 action movies, 2 romances, and 6 comedies. Person B watched 1 action, 9 romances, and 3 comedies. Notice what we did there? We haven't done any AI yet. We've just converted the messy, complicated real world into a structured data profile that a machine can actually read.
And that brings us to a really crucial definition. Mathematics is simply the first disciplined language of measurable reality. Think about it. Numbers allow us to compare. Is 8 greater than 1? Yes. And once we can compare things, we can start to discover patterns. We can group the action lovers together and the romance lovers together. This simple act of measuring, comparing, and finding patterns, that is the absolute root of all artificial intelligence.
Moving right along to Section 2, learning from mistakes, which is really the engine of intelligence.
So, once we have these patterns, what happens when those patterns change? How does a machine actually learn to get better at predicting them? Well, the crucial point here is that learning, at its very core, is just structured correction. Think about how you or I learn to throw a basketball. You make a prediction. That's your throw. You watch it miss a little to the left. That's your measuring the error. Then you change your stance for the next throw. You adjust. Machine learning follows this exact same 3-step loop. Predict, measure the error, and adjust. It's not magic. It's just practice guided by feedback.
In machine learning, the system looks at some input data, makes a guess, and then checks that guess against the true value. The gap between its guess and reality, that's the error. And here's the thing. Without that error, there is no feedback. And without feedback, there is absolutely no improvement. This repeating, relentless loop of correction is the true engine that powers modern AI.
Now, if you read articles about AI, you are constantly going to see the term loss function. And yeah, it sounds super intimidating, but let's bust that industry jargon right here, right now. A loss function is simply the mathematical way a system measures the gap between its prediction and reality. The human meaning? It's literally just learning from mistakes. A high loss means a big mistake. A low loss means you're getting closer to the truth. That's all it is.
Imagine you're standing on the side of a hill, completely blindfolded, and your goal is to find the deepest part of the valley below. You'd probably feel the slope of the ground with your feet and take a step downward, right? In AI, that hill represents the amount of error. The machine uses math to feel which direction reduces the error, and it takes a step downhill. It just keeps stepping over and over until it reaches the bottom of the valley. That lowest possible error point is the best possible solution.
All right, Section 3, the architecture of AI and how we go about scaling this intelligence.
So we know how machines learn from simple numbers and errors. Let's transition to modern AI and see how these simple error correction principles scale up to process something incredibly complex: human language and meaning. Here's a secret. Neural networks cannot actually read words. They only understand numbers. So how on earth do they grasp meaning? Through something called embeddings. An embedding takes a word and translates it into geometric coordinates in a vast mathematical space. And the brilliant part is that words with similar meanings are placed physically closer together in this space. So the literal distance between the coordinates for cat and dog is much shorter than the distance between cat and car. Distance literally becomes meaning.
But as you know, a single word isn't enough. Meaning changes depending on where a word sits. Think about it. Sitting on a riverbank means something totally different than walking into a financial bank to deposit some money. True language representation requires the word itself, its position in the sentence, its neighborhood of meanings, and the surrounding context. It's the whole shebang.
And this is exactly why the transformer architecture revolutionized AI. Older models, they used to read sentences word by word, often forgetting the beginning by the time they reach the end. Transformers absolutely do not do that. They look at all the words simultaneously. They use this mechanism called attention to draw a massive web of connections across the entire sentence, finding relationships and distant context instantly. It's kind of like having a bird's eye view of the entire paragraph at once, which allows the model to update the true meaning of every single word based on its neighbors. It's a real game changer.
Moving on to Section 4, Building AI Agents, going from just answering to actually acting. Now that our system understands language and can answer questions, what happens when simply answering a question is no longer enough? What happens when a system actually needs to take action in the real world? Well, that brings us to AI agents. And I absolutely love this quote from our source material. An agent is a system that follows a goal through steps. That movement across steps is the critical distinction here. An AI that just answers a question, that's a helper. But an AI that breaks a goal down, decides what to do first, acts, checks the result, and then moves to the next step, now that is a true agent.
For an agent to actually function in the real world, it needs a really specific set of components. It needs a clear goal. It needs memory to retain context. It needs tools like, say, the ability to search a database or check a calendar. It needs to track its state. And most importantly, it needs human review. Imagine a study assistant. If it just gives you a fact, it's a helper. But if it checks your calendar tool, schedules a revision session, tracks your past performance in its memory, and updates its state to waiting for student response, boom, now you have a fully functional agent. It's incredibly critical to understand the difference between memory and state, because people confuse them all the time. Memory carries selected past context. That's like knowing a manager prefers short, two-paragraph summaries. State, on the other hand, tracks exactly where the agent is in the present workflow. It's knowing that it has already pulled the data but is currently waiting on human approval before it sends the email. If an agent loses its state, it's literally like a person walking into a room and completely forgetting why they went in there.
And finally, Section 5, Trust and Human Judgment, the absolute final layer. Let's bring this whole journey back down to earth. We've built an incredible system that can translate reality into math, learn from mistakes, understand deep context, and act upon goals. But what is the final, ultimate layer of this architecture? It is trust and human oversight. The most critical question any team building AI has to answer is, when can the agent act automatically? Because movement creates responsibility. A bad plan can disrupt a schedule, and a confident but wrong AI response can hide a massive business error.
So the absolutely crucial point you must take away from this explainer is this. Autonomy is earned, not assumed. A machine learning model is not automatically wise. We let agents act automatically only when the task is low risk, well-tested, and completely reversible. For any high-risk action with real-world consequences, human review must come first, no exceptions.
To enforce this, we build operational guardrails. We use tool allow lists, so the agent can only access specific pre-approved systems. We use role-based permissions. We literally hard-code human approval checkpoints into the workflow, so the agent physically cannot proceed without a thumbs up from a real person. And we program safe fallback behaviors, so if the AI ever gets confused, it fails safely rather than just wildly guessing. Responsible AI deployment relies completely on these structured, human-defined boundaries.
Which leaves us with one final provocative thought. Over the course of this explainer, we've seen that AI is not magic. It's a brilliantly structured system of mathematics, pattern recognition, and error correction. But while machines can learn patterns and execute steps, true judgment, ethics, and accountability, those still belong entirely to us. So in a world increasingly filled with intelligent machines,
What decisions will you choose to keep human? Think about that as you navigate your own AI journey. Thanks so much for exploring with me today.